Okay, question number 3 involves kind of the 3 big strategies that were new for this chapter. Um, well, actually, it only has, we're using 2 of them. I can see twice here examples of where I might use looking inside. And then I also see this technique called fraction buster. So if you recall, we talked about looking inside, rewriting things, and undoing as ways of solving equations. And we also separately discussed on another day the idea of fraction busters, multiplying equations by something so that you eliminate the fractions. So let's go ahead and look at part A first. I can see that I'm taking the square root of something and I'm getting an answer of 3. Well, because I know something of arithmetic, I know that it is the number 9. If I take the square root of 9, that produces a 3, right? So what I need to do is I need this thing inside the inside the radical symbol to be a 9. In other words, I need 2x plus 3 to be 9. And by looking inside and asking myself, well, what does that thing inside have to be? I could think about this. And if I could force it to be the number 9, then certainly it would be a solution because the square root of 9 is 3. So from this point, what I can do is I can go ahead and subtract a 3 from both sides. So I get that 2x is 6. And then certainly I can divide both sides by 2. So x has to be the number 3. So when x is 3, you can see what it does here. It forces 2 times 3 is 6, plus another 3 is 9, and the square root of 9 is 3. So it forces both the left-hand side and the right-hand side to become 3. So down below here, I'll write in my answer spot, x is 3. The next one, again, this is an example of looking inside. If I look, my bases are identical, right? They're both a base of 2. And as I look up to my exponents, I can see on the one side my exponent is 2x minus 1, and on the other side my exponent is x minus 3. Well, if these two expressions, the left and the right-hand side, truly are equal to each other, the only way that's possible is if this exponent on the left-hand side is the same thing as the exponent on the right-hand side. They must both be the same. Well, how do I do that? Well, again, looking inside, I can say, look, I need 2x minus 1 to be the same thing as x minus 3. And if I can force those to be equal to each other, then certainly these two expressions will be equal to each other. So that's what we're going to do. We're just setting them equal and solving. If I take away an x from each side, I end up getting that x minus 1 is negative 3, and then I can add 1 to each side. And when I do that, I get x is going to be a negative 2. So my claim is that when x is negative 2, it forces these to be the same. Actually, I want to look at that. If I put negative 2 in here, 2 times negative 2 minus 1, that would be a negative 4 minus 1, which is negative 5. So I end up getting 2 to the negative 5th power. And over on the other side, when I plug in the negative 2, you can see this becomes, right, if this becomes negative 2 minus 3, that's also negative 5. So this becomes 2 to the negative 5th power. You might ask yourself, well, what is 2 to the negative 5th power, right? Well, remember, that is, I can show it in 2 steps, right? That is the same as if I multiply 2 to the 5th over 2 to the 5th, right? What I have here now, again, I'm multiplying just by 1. What I have in my numerator is the number 1 now. 2 to the negative 5th times 2 to the 5th is 2 to the 0 power, which is 1. Anything to the 0 power is 1. And my denominator of 2 to the 5th. So that's 2, 4, 8, 16, 32. So what I'm looking at here is 1/32. So when I plug that number in, I get 1 over 32 on both sides. Probably a little bit more than I needed to say, but again, the big strategy here is if your bases are the same, right, the only way that these two expressions can truly be equal to each other is if the exponents are the same. So I'm forcing the exponents to be the same, and when I force the exponents to be the same, the left and right hand side are the same. All right, the final problem that we have in this part is C. And this is an example of what we called fraction busters. And I can do this in 2 steps, or I can do it in 1 step. I'm going to do it in 2 steps. What I'm going to do is I'm going to space this out a little bit. So I've got 3 over x plus 5 halves, and that's going to equal 7 halves. And what I'm going to do is I'm going to choose to multiply both the left and the right hand side by 2x. So I'm going to introduce, and let me use a color for this. I'm going to introduce 2x over 1, multiply over here 2x over 1, and then over here 2x over 1. So what I've done is I've pushed this factor of 2x over 1 on through both sides of the equation. Every single term picked up a new factor of 2 and a new factor of x. Now as I look at each of these and rewrite them, I can see that I have some giant ones that are formed, and I'm going to use those to simplify this equation. The first case, I see when I have x over x, that is 1. So I'm left with just 6 here. On the other side, you can see that I have a 2 over 2. That's 1. So there's a giant 1 there. So this leaves me with 5x. I'm just switching the order. Instead of writing x times 5, I'm writing 5 times x. And then finally, the other side is in terms of equal, right? You can see that there is a factor of 2 over 2. So I'm left with 7x. So this is a pretty straightforward equation to solve, right? I'm going to take away 5x from each side. And when I do that, I end up getting that 6 is 2x, and if I divide both sides by 2, I end up getting that x is 3. So x is 3 is my solution. I'll make sure I write it down here as well.